Today I'll be speaking about eBPF. The title of my talk is eBPF, Android Reverse Engineering Superpowers. So I'm a security consultant at Centurion Information Security, and here are some of the places that you can find me online, like my blog or my GitHub account. So the agenda for the talk today will be as follows. I'll be talking about what exactly is eBPF, why eBPF is interesting from the perspective of reverse engineering Android applications. I'll talk a little about how to set up eBPF on Android, and finally, how do you get started writing eBPF programs? So what exactly is eBPF? eBPF stands for Extended Berkeley Packet Filter. And the idea of eBPF is that it's a framework for tracing a Linux system. And if any of you have used Solaris dtrace before, you can think of eBPF as a Linux version of dtrace. And eBPF requires a relatively new Linux kernel. The officially supported kernel is 4.1 and above, but later versions of the kernel adds new features. So if you're running an eBPF program, ideally you should run the latest kernel supported by your device. And the idea of eBPF is that you write some custom code that triggers whenever something happens in the system. And the workflow of writing an eBPF program is you write code, you use the compiler to compile it into bytecode, you load the bytecode into the kernel through the BPF syscall, and you execute the bytecode in kernel whenever something happens. And there are 4 different event sources that you can attach a eBPF program to. You have something called kprobes, you have uprobes, you have trace points, and you have USDTs. Kprobes and uprobes are relatively simple to understand. You attach a eBPF program to a kernel function or a user space function, and that program triggers whenever you enter into a kernel function or you return from the function. And uprobe is kind of like the user space version of a kprobe. Trace points are used to attach an eBPF program to an event within the kernel. And there are a large number of events that are exposed by the kernel, and the events depend on the specific version of the kernel that you're running. So if you have a Linux system, you can actually print out the supported events by listing out the syskernel debug tracing events directory. So this is a screenshot of my Linux machine running Ubuntu 18.04, and these are all the supported trace points. You can see events related to syscalls, to power events, to Wi-Fi. So whenever something happens in the whenever something happens in the Linux system, for example, you attach to a Wi-Fi, you can write an eBPF program to do something. And USDTs are kind of like the user space version of trace points. So if you're writing a user space application, you can insert a special function within your application, and you can attach to it. So this is useful, for example, if you are running code in a production system and you want to find out what exactly your program is doing. And eBPF provides a way for user space program to talk to the eBPF program, because it's not very useful if you, for example, collect some data in the kernel, but you cannot extract that out. And the way to do things is that you use this BPF perf output function, which sets up a very fast ring buffer between the kernel space and user space, and you can transfer data to and from it. And there are different data structures that you can use, so depending on exactly what you're doing, you can use arrays, you can use dictionaries, for example. And you can create multiple ring buffers for per eBPF program, so you can have multiple channels communicating between user space and kernel. So you do not want to write eBPF bytecode by hand, even if you can if you want to, but it is very tricky. So what you should use is you should use the BCC compiler, which is written by the maintainers of eBPF in the kernel. So you can be pretty sure that the BCC and the kernel supported functions are in sync. And running arbitrary code in the kernel is very risky, which is why eBPF has something called a validator that tries to ensure that your eBPF program is safe to run in the kernel. And the eBPF validator tries to ensure that your program will terminate. So you can't have an infinite loop in your eBPF program. So the way that it does it is that it does a depth-first search on the eBPF program's control flow graph to ensure that there are no things like infinite loops or undecidable loops at compile time. And the eBPF validator is very strict, and it errs on the side of rejecting potentially valid programs, which is pretty annoying when you're trying to write an eBPF program, because you can write a program that you know for certain is safe, but the eBPF validator does not think that it's safe. So this is one of the more tricky things about writing eBPF programs. And the validator also does things like ensuring that the stack and register state after every instruction is executed is safe, and validate things like there are no out-of-bounds reads. And the main usage of eBPF currently is instrumenting production Linux systems, especially if you are running a distributed environment like Kubernetes. It is very difficult to find a reproducible test case for an issue that you might find in production. So what people like to do is they like to instrument all of their production systems with eBPF to collect statistics about the system so that they can make educated guesses about what is actually happening. And eBPF and BPF can actually be used to implement things like firewalls in the kernel. So why are we interested in eBPF specifically? Because the talk is about Android reverse engineering. To understand why eBPF is useful, we first need to understand what reverse engineering is. And reverse engineering is essentially about understanding an application. There are three main categories of techniques. You have static analysis, where you decompile or disassemble your application with an program like IDA Pro or Ghidra. There's debugging, where you use GDB or WinDebug, or a instrumentation framework like Frida or Intel Pin to debug the program at runtime. And you have things like behavioral analysis, where you treat the application as a black box. So you might do things like using strace, ltrace, or procmon to monitor what the program is doing at runtime. And when there are reverse engineering techniques, people try to make it difficult for reverse engineers to understand what the application is doing. To counter things like static analysis, application developers might employ techniques like obfuscation that makes it difficult to understand what a program is doing. So obfuscation works by messing up the program's control flow while retaining the same program semantics, essentially meaning that the program does the same thing, but you can't read what it's doing. And things for runtime debugging, dynamic analysis like debugging or behavioral analysis, an application developer might employ anti-debugging techniques, or on mobile devices, especially popular are root and jailbreak detections. Because a lot of this analysis requires you to have root or something root-like on your system to run. And the OWASP MSTG, the Mobile Security Testing Guide, actually documents some of the more common anti-reverse engineering techniques you might find on a mobile device. If you're looking at Android specifically, an Android app might employ a combination of the following tricks. It might have root detection to ensure that it only runs in a non-rooted environment. It might employ anti-debugging techniques, so you cannot attach a Java debugger or a native code debugger onto your application. It might employ obfuscation to make it hard for static analysis to work. And it might employ things like for integrity checks so that you cannot simply repack the APK. And a very particularly annoying trick when it comes to anti-debugging is tricks that prevent the ptrace syscall from being used. Because a lot of your common tools like GDB, like strace, like Frida, they all rely on being able to ptrace your target process. And a very common anti-ptrace technique abuses the fact that you can only ptrace one process can only be ptraced by another process. So you cannot attach a tracer to a process that is already being debugged. And what applications might do is they might fork off a child process that the only thing that the child process does is call ptrace on the parent. So I lifted some code from the OWASP MSTG. You can actually find that in the Mobile Security Testing Guide. And what this function does is essentially the parent application forks off a child process, and the only thing that the child process does is call ptrace on the parent. So as long as the child process is alive, you will not be able to attach any debuggers or Frida, for example, onto the parent application. In this very trivial example, if you just kill off the child process, you can continue debugging the parent. However, in practice, an application might employ tricks that ensure that the child process remains alive as long as the application is running. So the application might do things like fork off multiple child processes tracing each other. They might monitor for running processes so that you cannot simply just kill off a child process and debug. And applications that have multiple reverse engineering tricks implemented can be very difficult to analyze. For example, if an application is obfuscated and employs anti-debugging, you will not be able to understand what the application is doing by static analysis. and you cannot start to debug the application using a debugger. So how do you actually start to understand, how do you actually start to get a foothold into understanding what the application is doing? This is where having very low-level capabilities, essentially kernel-level capabilities, are very helpful to debug the application, because you want capabilities at the level that the application cannot subvert. And in the case of mobile devices, Android devices, this means kernel-level code, because an application usually does not run on an environment where you have root, so the application cannot load stuff into the kernel to do checks. So previously, having kernel-level capabilities require writing a kernel module. And if any of you has done Linux kernel driver development before, you know that it's a very tedious process, because if you write bad code in your kernel module, the most likely outcome is crashing your device. And the development process of writing a kernel module can be very tedious, because you write it on your host machine, you need to compile it into executable code. So if you're running on an ARM device, running on Android device running on ARM, and your host machine is x86, you need a cross compiler, which is not difficult but a bit annoying to set up. And you have to transfer the kernel module onto the device. You have to load it and hope it works. If it doesn't work, you have to repeat the whole process over again. So when I came across eBPF, I thought this was the perfect solution for running code in the kernel, because it allows you to have a very efficient process for writing code. You can iterate pretty quickly. So how do we set up eBPF on Android? eBPF works on Android because Android runs a relatively standard Linux kernel. I think for the later versions of Android, it's actually tracking the mainline Linux kernel and not running on some separate tree. So all of your Linux debugging tricks should work on Android. However, it did take me a while to figure out how to get everything working, because a lot of the documentation on the eBPF toolchain assumes that you are running on a standard Linux environment and not an Android device. To understand why this is tricky, you need to understand the requirements for BCC, which is the standard eBPF compiler toolchain. BCC is a LLVM-based compiler, so right out of the gate, this means that you need to have LLVM on your Android device. And it also requires things like kernel headers to be present, and it requires Python to be present on your system. And these three things are not something that you'll typically find in an Android device. So luckily for us, there is a project called ADEB that makes it pretty simple to set up the BCC toolchain. And this ADEB stands for Android Debian. So it's maintained by a guy working at Google, if I'm not wrong. And what it does is it sets up a Debian environment running on your Android device through the use of chroot, essentially. And when you install ADEB on your Android device, it comes with BCC by default and a few other useful tools. So you have like Vim for code editing. You even have access to apt-get, so you can install any Debian packages on your Android device. And this is very handy when it comes to analysis, because you don't actually have to compile Android-specific versions of binaries. You can just grab it from the Debian repository. However, ADEB still requires the kernel with the required kernel configs turned on. And what ADEB requires is a kernel version of 4.9 and above, and it requires these 6 different kernel configurations to be enabled. The problem is that no current version of Android supports the necessary configurations. I have not looked at Android Q for now, but Android Pie and below, none of them support this. So what this means that you have to build your own kernel to get BCC running. And the process of building a kernel will depend on the environment that you are running on. So if you're running on an emulator versus an actual device, you might need to grab different kernel source trees. And if you're running a manufacturer-specific version of a device, so you're running a Samsung device, you might need to apply some patches from the manufacturer onto the kernel. So I will not go into detail about how to build a kernel, because there's a lot of documentation out there. But once you have done that and you have your Android device running on that kernel, all you need to do is you need to run the ADEB prepare command. So there's a lot of documentation at the ADEB repository, but the main command that you need to know is the ADEB prepare command, which will prepare a file system containing all your Debian utilities and build it against the kernel source tree. And there are a few different useful flags, such as the --arch flag, which will allow you to specify the architecture that your device is running on. So x86, AMD 64, ARM 64, you will need to pass in a different flag. And if you want to save this process will take probably 5 to 10 minutes to run, to build everything. So if you want to save that output, you can use the build tar flag to save it into a gzip file. If you have already prepared a Debian environment, you can use the second command, the -- archive parameter, to pass in the pre-built file system. And once you have done that, you have loaded ADB onto your kernel device, you can run ADB shell on your terminal and get a Debian environment on your Android device. And BCC by default comes with a few useful utilities like FileTop and OpenSnoop. So just a quick video, hope it's not too small, but I am just running ADB shell, which will drop me into a Debian environment. You can see I'm running the OpenSnoop command, which traces all the open syscalls on the device. If I launch an application, you'll see a lot of outputs start printing out because it is essentially tracing everything that the application is loading while you launch it. So OpenSnoop is one of the pre-built utilities that ship with BCC, and there are multiple ones that traces different syscalls, different files being opened, your network processes, and so on. So how do we actually write eBPF program? Because if we have custom logic that we want to implement, we need to write our own programs. The way that you write an eBPF program with BCC is that you write it in Python. You import the BCC module, you'll build up a string containing the eBPF program, and you'll pass it into the module. And the BCC module invokes LLVM behind the scenes, compiles the program into bytecode, and loads the bytecode into the kernel. As an example, I will show you how to write an Hello World program that attaches onto the OpenNet syscall because we want to trace all the files being opened on the system. So I'm essentially re-implementing the OpenSnoop utility that comes with BCC. And what we want to do is we want to send out the file name that's being opened from the kernel into user space and print out the output. So this is an eBPF program. The first section up there that I've highlighted, we are defining a structure that will contain the data that we want to transfer into user space. In this case, it will be a structure containing a file name character array because we are interested in passing the file name being open to the user space program. And we are using the BPF perf output function to open up an event. And this is how we transfer stuff from kernel space into user space. Next, we define a function using the special kprobe __ syntax that tells BCC that this is a kprobe function that we are defining. And you'll see that there are multiple parameters to this function. These are all parameters to the OpenNet syscall. So if we want to hook a certain parameter, we'll need to pass in the parameter. But if we are not interested in for example, the last two parameters, we can leave that out. So you don't actually have to fully specify the function signature. And in the program of the function, we are initializing a open_data_t structure that we have defined previously. And this is the structure that we'll be using to transfer data from kernel to user space. Next, we'll use the BPF_probe_read function to copy out the file name from the kernel, from the function parameter into our initialized structure. And finally, we use the open_event.perfsubmit function to transfer that initialized data structure from kernel to user space. In our Python program, we'll define a callback function that essentially runs every time user space receives an event from the kernel. And in this callback function, we are simply printing out the output of our data structure. We initialize a BPF program in Python. We open up a perf buffer. So this is how we initialize the communication channel between kernel and user space. And we will pull the program in an infinite loop. So whenever something is transferred from the kernel to user space, we immediately call our callback function, which prints out the output. So if I run the program that we have just written, right, so I'm running the Hello World Python script. It will take a while to load, but once it does, whenever you launch an application, you'll start printing out all the output of the OpenNet syscall. And you might notice some Chrome-related files being opened because we are opening up the Chrome APK. Next, I would like to talk about code generation, which is a common pattern that you will see in eBPF programs. And it is very useful if there's a part of the program that you want to change every time you invoke the Python script. Because what you have to remember is that the Python script compiles the eBPF program from scratch every time before it loads it into the kernel. So if there's a part of the code that you want to change on every invocation, for example, you want to add PID filtering. Let's say I'm only interested in the syscalls being called by a specific process, PID, or process name. I can add some code using code generation to add that logic in. And it is also very useful to get around certain eBPF limitations. For example, you can't have loops in your eBPF program. So what you can do is you can use code generation to emit that section of the code 3 times, for example. So this is the same program as before, but what I added was a PID underscore filter placeholder string, which I will then replace with actual C code later on. So the replacement function, what it does is it takes the PID underscore filter placeholder and it replaces it with some C code that checks the current PID that is being, that's calling the syscall. If it matches what we want to filter, we continue, otherwise we'll just return. And you can see that this, I'm actually using the sysargv Python function. So what the PID that I'm filtering is based on the argument that I passed into my kernel program, into my Python program. So if I run the Python script now, you see that I'm launching the YouTube application. So what I'm doing is I'm doing a PS and grep to find out the PID of the YouTube application. In this case, it will be 6921. I'll pass that PID into my Python script, which will start doing the syscall tracing. And you can see that it only starts printing out the file names that are related to the YouTube application. So in this way, you can do very specific filtering on what exactly you want to trace. Do you want to trace one application? Do you want to trace multiple processes and so on? So what I did was I put everything together into something called strace. So I'm trying to re-implement the full strace utility that originally relies on having ptrace with eBPF. So I've implemented several modes like tracing mode, which will simply list out all the syscall that's being used, or things like aggregate mode, which does a counter. You can do things like filter by PID or process name. You can filter only the syscalls that you're interested in. So for example, you're only interested in file-related syscalls or network-related syscalls. You can ignore the rest of the noise and just focus on what you want to trace. And the disclaimer is that I'll publish the code, but it's pretty ugly code. I'll hope to clean it up sometime, but it works. So this is the code running. So you can see that all the options of the programs I've implemented, the trace mode and aggregate mode. So what we want to do is we want to start tracing out all the syscalls being made by the YouTube program. So I'll just specify the name of the APK file. I'll start aggregating the syscalls. So if I launch the app, you'll not see any output being printed. But if I type Control-C, what the Python script does, it will do a count of all the syscalls on the system. So with this, you can get an idea of what the application is trying to do. Is it making a lot of file requests? Is it making a lot of network requests? And if you want to know more details about the exact syscalls that the application is doing, you can do trace mode, which will start printing out a lot of output related to the application. And you can do filtering. So for example, you're not interested in 10 of the syscalls. You can filter out a lot of the noise. The final interesting capability that you can do with eBPF is that you can actually modify user space memory from the kernel. And this is done through the bpf underscore probe underscore write user function, which has a signature that's very similar to memcopy. There's a limitation from it. There's a limitation that you cannot actually write to memory that is not writable. So for example, you cannot simply overwrite the text segment of a process. However, you can write to stack memory and you can write to heap memory. So if any of you have done exploit development before, you know that this is essentially enough to get arbitrary code execution because you can do a ROP chain. So I'm not going to show a ROP chain, but as a very simple example, I will show how you can use this capability to bypass a very simple root detection technique. So what The example I'll be looking at is the Uncrackable Level 3 APK from OAuP's MSTG. And what this APK does for root detection is it looks for the presence of certain files on your system. The files that it looks for are listed here, and what you can see is that they're all related to the various routing frameworks. It looks for the presence of the SU binary or the superuser APK file. If it detects any of those files on your system, it will bail out, otherwise it will continue running. And it tests for the presence of those files using the fxs at syscall. And you can, of course, find this information either by unpacking the APK, or you can use something like the strace utility I've demonstrated before to find out the syscalls that are being used. And the fxs at syscall second parameter takes in the path name of the file that you want to test for the presence. And we can use the BPF probe write user function to overwrite that character array to point to a file that is non-existent on the system. So I'm just going to give a demonstration of the code. So if we launch the application now, you'll see that it says root detection detected. However, if I run my Python script that hides the presence of those files, I will pass in the name of the APK. It will start hiding all the SU binaries. If I launch the app now, you can see that I can actually use the application normally, and the script actually prints out all the files that is hidden from the system. And the cool thing about using eBPF instead of something like Frida to do this bypass is that you can apply this trick system-wide. So you can apply it to every single application running on your system. So for closing notes, I would like to talk about some limitations of eBPF. The biggest problem when writing an eBPF program is that the validator or the verifier can get in the way of writing very complex or substantial programs, because things like no infinite loops, no function calls are very strong limitations. And the second problem is that it requires familiarity with the Linux kernel APIs, because you are doing tracing at the kernel level. And the problem with writing kernel code is that there is no stable kernel API. So you might find that a BPF program working on one version might not work when you upgrade your kernel. So the recommendation I have is probably to stick to a stable kernel version when you're doing tracing, unless you really need a feature from a newer kernel. And an eBPF program cannot write to kernel memory, because this is a very strict requirement, because you cannot ensure that a program is safe to run if you can just mess up kernel memory. So if you want the capability of writing to kernel memory, you have no choice but to write a kernel module. And when you're doing syscall tracing, a very big problem will be time of check, time of use issues. This is a very well-known problem when writing Linux kernel drivers. So there's a LWN article, I believe, from 2008, and you have the same problem today. Because what a syscall is a boundary between user space and kernel, and user space memory can change. So if you are tracing the syscall at the very entry to the kernel, that function pointer will be pointing to a memory that can be changed by any user space program. So you might have race conditions where at one point of your eBPF program, you assume it's pointing to a certain location, but at the later point of the execution, it's actually pointing somewhere else. This is usually not a problem when you're tracing normal or cooperative applications, but if you are tracing an application that tries to hide some stuff, they might fork off a different process that is messing with their memory. So the way to get around this issue is that you don't trace at the syscall level. So you look at kernel functions that are a few levels deeper within the kernel. However, the good thing about eBPF is that it offers a lot of power while being relatively simple to write. This is especially when you are more familiar with the Linux kernel APIs and you know what the limitations of the verifier or validator are. And especially if you have some bootstrap programs that you can just copy and modify to do certain things. It is very good for ad hoc tracing and scripting, especially when you have Vim running on your Android device, so you can simply modify code on that device and run it. What I would like to see is a set of eBPF programs like the one in BCC, but they are more focused on the security or reverse engineering space, because a lot of the utilities out there that are written are more focused on performance tracing. And there are multiple useful resources when you want to learn more about BCC and eBPF. The first one would be the BCC reference guide, because BCC is written by the same people maintaining eBPF in the kernel, you can ensure that their documentation are pretty much accurate. And when it comes to Linux programming references, there is of course the man command. This might sound stupid, but it's actually very, very useful because most of the Linux kernel documentation can be found in man pages. And there is a book coming out in October called BPF Performance Tools, written by the same guy that is maintaining BCC and eBPF. So I'm looking forward to reading that book. I don't know how good it is yet, but hopefully it's very useful. You can find the code examples I've shown at the GitHub repo, and if you're interested in the slides, you can copy the link. Very early, so are there any questions?
We have 10 minutes for questions. Do you have any questions?
Yeah, you can always find me later if you want to talk more about this.